All right, so this is probably a pretty extensive lesson on where we really start to introduce trigonometric ratios in terms of angles and center position. Until now, we haven't really worked with sine, cosine, or tangent much. Plus, we'll be introduced to 3 other trigonometric ratios. So with that said, let's remind ourselves of something that was part of pre-calc 11, so hopefully sounds familiar, which is a way of defining sine, cosine, and tangent, but not in terms of right triangles, in terms of an angle and center position. So by default, we tend to think of sine as being opposite over hypotenuse, but that only makes sense if you're referring to a right triangle. So what if we're referring to an angle and center position? We can redefine sine, cosine, and tangent if we just know of a single point on the terminal arm of an angle and center position, and the distance from that point to the origin we call r, which again, r for radius, because if you imagine that point being tracing around as we have a rotation, it would trace out a perfect circle of radius r. That said, sine can be defined instead of opposite over hypotenuse as y over r, cosine x over r, and tangent y over x. So I'm saying this fairly quickly because I'm hoping this sounds familiar. It's just a different way of defining sine, cosine, and tangent, and it works, they behave the exact same way as with right triangles. If you think in the first quadrant, because if you're dealing with a right triangle, theta has to be between 0 and 90. But when you think of rotations, you can go past 90 degrees. And so again, hopefully that sounds familiar. As well, what also should sound familiar is that if we imagine p theta being the function that tells you the coordinates of the intersection between an angle and center position and the unit circle, then the x coordinate is always the same as the cosine of your angle, and the y coordinate is always the same as the sine of your angle. All right, what's probably not review are the 3 reciprocal trigonometric ratios, which are just other combinations of x, y, and r. And so CSC stands for cosecant, and that is r over y. SEC stands for secant, which is r over x. And cotangent, which the abbreviation is COT, is x over y. We call these the reciprocal trigonometric ratios because if you compare it to what I have above, they're all reciprocals. So, of what you see above. Now, these 3 reciprocal functions, we don't deal with nearly as much as the primary trigonometric functions, but we'll start to see them now going forwards. And really the main thing is to remember that cosecant is the reciprocal of sine, secant is the reciprocal of cosine, and cotangent is the reciprocal of tangent. Not the inverse, the reciprocal. All right, inverse function is very different. Inverse undoes things. For an inverse trig functions, the input is a ratio, the output is an angle. These aren't inverses, they're just different combinations of x, y, and r. All right, and as well, the cast rule is something you probably learned about before. And really that states that, actually I'll start with this, that all your trigonometric functions, sine, cosine, and tangent, in the first quadrant, if you have an angle in standard position that ends in the first quadrant, they all are positive. The sine, cosine, and tangent of those are all positive. All right, in the second quadrant, only sine is positive. I'll put the sine of theta. Cosine and tangent are both negative in that quadrant. In the third quadrant, only tangent is positive. And in the fourth quadrant, yes, you guessed it, only cosine is positive. And so notice how I've been highlighting things. You can remember all of this. You can easily memorize all of this if you can memorize those 4 letters in those 4 orders. A in the first quadrant, S in the second, T in the third, C in the fourth. We tend to call this the cast rule. It's not really like a proper theorem or anything. Just a quick way of memorizing where different trigonometric functions are positive or negative in different quadrants. So again, if you can just memorize those 4 letters and those 4 orders. Quite often people memorize it as all students take calculus, ASTC, which again is not true. All students don't take calculus, but whatever works. All right, so pretty much everything I said here has been review, aside from those reciprocal trigonometric ratios, which really are just, it's not a big deal, just 3 new functions, reciprocals of what's above. Let's start trying to put all this together. And so first, what I have here is, I say a point P, which is at -3, 5, is a point on the terminal arm of an angle in standard position. Determine the exact value of all 6 trigonometric ratios. I'll do that first. Then I'll talk about the second part, which is then determine one possible measure for theta in degrees and in radians. All right, so if I want to find all 6 trigonometric ratios. So for example, I want to find the sine of theta. I want to find the cosine of theta and the tangent of theta. As well, I want to find the reciprocal ones, which I'll get to in a moment. So how do I do that? Well, the sine of theta, if we think of sine, what is sine? In terms of angle and standard position, sine is y over r, which stands for the y coordinate, some y coordinate of an angle in standard position. And so I can see that's 5 right there. And so r is the distance from that point to the center, to the origin. The distance I'm highlighting in orange. Sorry, in green. And so how do I figure that out? Well, I can use the Pythagorean theorem. Like I can imagine there being a little right triangle right here, which I don't know what r is, but I know the height is 5. I know the horizontal distance is 3. Or I can just use I can go straight to this. I can say x squared plus y squared equals r squared, which is also the equation of a circle of radius r, which is the Pythagorean theorem. So in this case, I get 3 squared plus 5 squared equals r squared. And so 34 equals r squared, or r equals root 34. Now, I know I will say you may be tempted to put plus or minus right here when you go from this step to this step, but remember r is a distance. It's the radius, and distances are always positive. So I don't want those. There you go. The radius is root 34. So the sine of this angle is 5 over root 34. So I don't know what the angle is, because again, you may think the angle is going from here to here, but we don't know if it is. It could be going backwards. It could be going around and around. We don't know how the terminal arm ended up in that spot. It doesn't matter. It doesn't matter what the angle is. All that matters is where the terminal arm ended up. If it ended up going through -3, 5, the sine of the angle will be 5 over root 34. And what is that, how is that useful? We'll get there. Cosine. Cosine is x over r. So the x coordinate is -3, so it's -3 over root 34. Notice that the cosine of this angle is negative, which we saw from before is always going to happen in the second quadrant. And tangent is y over x. So in this case, it's 5 over -3, or I'm going to write as -5/3, same thing. Again, tangent is always going to be negative in the second quadrant. All right. Those are the 3 primary trigonometric ratios. What about the reciprocal ones? Well, those can be really easily found if we just kind of compare each of these, the reciprocals. The reciprocal of cosine is cosecant. And so the cosecant of this angle is going to be root 34 over 5, the reciprocal of what I had before. The reciprocal of cosine is secant. And so the secant of this angle is going to be negative root 34 over 3. And the reciprocal of tangent is cotangent, so the cotangent of this angle is -3/5. That quick. Again, these reciprocal functions, as long as we know they're not inverse, we don't mix them up with inverse functions, they're actually pretty easy to deal with. We don't see them much. They're just, again, literally the reciprocals of sine, cosine, and tangent. All right, that's the main part. So now it does say, then, determine one possible measure for theta in degrees and in radians. And so, like I said, I don't know what the angle is, but let's think of one possibility. Let's think of this possibility we see right there. I've drawn in blue. Let's call that theta. Let's say that's the angle. To find all these answers above, it didn't really matter how it got to that point. But what is that angle? Well, one thing we could be tempted to do is to use any of our trig functions here backwards. Because we know the output, we want to find the input. So let's try with cosine. Sorry, sine. Let's try sine first. Let's try the sine. Let's find the inverse sine of 5 over root 34. And I'm going to stick with actually just degrees here. And so let's look at the inverse sine of 5 over root 34. And if you do that, let me get my calculator out actually. Okay, so inverse sine of, where's my numbers again? There we go, 5 over root 34. And it says 59.03 and so on, so about 59 degrees. Okay, so I'll say about 59 degrees. So that's not wrong, but it's wrong for me to say theta is 59 degrees. If you look at my angle theta, how can that be 59 degrees? It's clearly not. So if I do the same thing with cosine, I'm going to get something different. In fact, if I use the different ratios, I'm going to be getting different values each time once I'm out of the first quadrant. So only in the first quadrant will I get the exact same value for the inverse sine, inverse of cosine, inverse of tangent, only if I'm in the first quadrant. So I'm not even going to bother doing the same thing for sine and cosine. Because that 59 degrees does tell me something. So it's first of all, I got to realize there's no way this angle from here to here is 59 degrees. But what that 59 degrees is, it tells me that that's my reference angle actually. My reference angle is 59 degrees. And why is that? Because if I think in the first quadrant, there is a point at 3, 5, and that will be a 59 degree angle. And so the ratio for that angle and the ratio for this angle for sine is the exact same. So how on earth can the calculator know we're dealing with the second quadrant? It can't. It just gives us one value. So let me erase all this mess I made here. But it's actually pretty complex. And again, when we just deal with angles between 0 and 90 degrees, we never have to deal with this fact that once we get past 90 degrees, our calculator will give us different possible angles depending on which ratio we're using, even though we're looking at the same angle. And so that said, that 59 degrees is very important to me. That's my reference angle. In this case, it's not my actual angle. And so once I know it's my reference angle, now I can say, therefore, theta, I can just visualize for my graph, theta must be 180 degrees, take away my reference angle. So it must be about 121 degrees. As for radians, I'm going to leave actually the radians for now. But that said, notice I did a lot of things here. I did very few calculations. I used my calculator once for inverse sine. But again, I don't think anyone's going to say this is easy. OK, what I want to do now is write down basically our special angles for sine, cosine, and tangent, except in radians. Now, in degrees, 30, 45, and 60, you can all connect directly back to your special triangles. So I'm going to start with those. So the sine of pi over 6, which is 30 degrees, is 1/2. The cosine of pi over 6 is root 3 over 2. The tangent of pi over 6 is 1 over root 3. That's all 30 degrees. The sine of pi over 4, which is 45 degrees, is 1 over root 2. Cosine is 1 over root 2. Tangent is 1. For 60 degrees, pi over 3, sine is root 3 over 2. Cosine is 1/2. Tangent is root 3. So all of those, we now just want to memorize. All of these you can figure out by drawing out a special triangle, 30, 60, 90, and going to 1, root 3, and so on. But at this point, going forwards, we just need these memorized. If we have to keep drawing this out, we are bogging ourselves down with details that are kind of, at this point, need to be just kind of established. And so all of those there, besides being in radians, go directly back to things you've learned before. As for 0 and 90, which is the ones above, the sine of 0, you can't figure out using a special triangle, but you can figure it out by looking at an angle in standard position. And a 0 degree angle would end up right here, and looking at the coordinates of x and y. And so again, once we get past 0 or 90, our angles, or right triangles don't make any more sense anymore. But we can think in terms of angle and standard position, or just for now, just memorize. The sine of 0 is 0, the cosine of 1 is 1, the tangent of 0 is 0. And for 90 degrees, the sine of pi over 2 is 1, this cosine of pi over 2 is 0, and tangent of 90 degrees is undefined. If you look at these as well, there's actually lots of nice patterns. If you look at cosine, the values get larger each time, up to 1, and cosine does the exact same in reverse. Cosine just goes the exact opposite way. So once you've memorized sine, you really can memorize cosine as going the other way around. Tangent actually has a nice, has some nice little things where 1 over root 3, 1, and root 3, these are reciprocals of one another. 1 is a pretty important one to remember. The tangent of 45 degrees is 1. Again, if we take a long time, going forwards, if I ask if we need to think about what the tangent of 60 degrees is, and we have to start drawing out right triangles, we're not going to be able to move forward properly. So at this point, this is so important. Memorize these, all of these. Memorize them like you memorize the times tables back in elementary school. You want to, if you have to think about what the cosine of 90 degrees is, you want to know it's 0 in a few seconds, literally just a few seconds. Okay, memorization is not hard. It just takes a bit of practice and a bit of deliberate practice. Okay, because this most students find hard. Determine the exact value of these without a calculator. How can I find the exact value of cosine of 13 pi over 6 without typing the cosine of 13 pi over 6 into my calculator? So let me show you. I'm linking lots of little things together. There's no complex calculations, but most students find this quite tough. So first thing I want to do is think about which quadrant is 13 pi over 6 in. And for me to figure that out, it's probably helpful for me I could change this into degrees, but the key thing is realizing it's pi over 6, which is 30 degrees, times 13. Right, oh, that's not what I want. It's 13 times 30, which you could work out is 390 degrees. Or, again, I don't want to think we always have to go to degrees. Notice if it was 12 pi over 6, if it was 12 pi over 6, that would be the exact same as 2 pi. And that would be going all the way around once and stopping right here. Well, it's not 12 pi over 6, it's 13 pi over 6. It's 1 extra sixth of a pi in radians around. So that means, if I just go back here, I know this rotation must start here, go all the way around once, that's 12 pi over 6, plus an extra 6 pi, extra 30 degrees. And so I don't really need to convert to degrees to know where this is fairly quickly. Now I know it's in the first quadrant, and I know the cosine of any angle in the first quadrant will be positive. So I know this is a positive number. Okay, but positive what? Next, there's not much left. Next, I need to figure out my reference angle. Well, my reference angle is pi over 6, or 30 degrees. How is that helpful? Because once I just think about now, what's the cosine of my reference angle, I'll know my answer. Because once I know it's positive, like I've said before, it doesn't really matter how a rotation gets to a particular point. Now that I know this is coterminal with 30 degrees, all I have to think about now is essentially what's the cosine of 30 degrees, and then I know my answer. And the cosine of 30 degrees, from just looking at what we looked at before, is root 3 over 2. So I'll say the cosine of 30 degrees, or I'll say the cosine of pi over 6 equals 30 degrees. And so once I have that, ideally from memory, then I know this is also going to be, sorry, not 30 degrees, root 3 over 2. Then I know this must be root 3 over 2. So the cosine of 13 pi over 6, or the cosine of 390 degrees, is root 3 over 2. Okay, so what I did is I found the exact value of a ratio in radians, but that's not really the key difference. You could always change it to degrees without using a calculator by connecting all the things we talked about before. And so I said most students find this challenging. And so what's this? Tangent of 5 pi over 4. First, let's think about which quadrant is it in. And I would realize it's pi over 4, which is 45 degrees, but 5 of them. So 1, 2, 3, 4, 5. I know it must be end up right there. That's one fairly quick way of knowing where 5 pi over 4 is. So I now know, without even turning this into degrees, that 5 pi over 4 radians will end up in the third quadrant. And I know in the third quadrant, tangent is always positive. So my answer is going to be positive. All that's left now is to think about positive what? Whatever's going to go here is going to be the same as the tangent of my reference angle. So once I know what the tangent, once I know my reference angle is, I just got to think about what's the tangent of that reference angle. Whatever that number is, goes right there. So what's my reference angle? My reference angle is pi over 4. Like literally, I figured out this rotation by going 5 of these pi over 4s. So I know this is pi over 4, which is 45 degrees if you want. And so now I've got to think about, okay, what is the tangent of pi over 4? What is the tangent of 45 degrees? That is 1. And so I know the tangent of 5 pi over 4 is positive 1, or just 1. Okay, let's try another one. Notice again, very little work on paper. Very few calculations. The secant of pi over 3. For this, all I first need to think about is, okay, what is secant the reciprocal of again? Secant is the reciprocal of cosine. So let's think about just cosine. Really, for the majority of this question now, I'm going to think about cosine. And what's pi over 3? Well, that is exactly 60 degrees. So 60 degrees is right here. So my reference angle is also 60 degrees. And so again, let's think about cosine. What is the cosine? Well, maybe I'll say this. In the first quadrant, cosine is positive. And so I know my answer is going to be positive. And so what is the cosine of 60 degrees? Or what is the cosine of pi over 3? The cosine of 60 degrees is 1/2. So therefore, the secant of pi over 3 is the reciprocal of 1/2, which is 2, or 2 over 1. And there's my answer, positive 2. And again, I don't even need that plus sign. So the secant of pi over 3 is 2. And notice, in terms of secant, all I have to do is just think about, okay, what's that the reciprocal of? It's the reciprocal of cosine. And really my question was just dealing with cosine. Where's cosine positive? What's the reference angle? Everything's about cosine. At the very end, I brought it back to secant. Again, simple calculations. I don't expect you to find the actual work altogether simple. Here's the last one before final problem. So cosecant of negative pi over 6. So cosecant is the reciprocal of sine. So I'm going to think about the sine function. Next, which quadrant is negative pi over 6, which is negative 30 degrees? Well, I can visualize that quite easily. That must look like this. Okay, and in this quadrant, sine is negative. So my answer here is going to be negative. Okay, negative what? Well, I got to think about my reference angle, which is pi over 6. And think about, okay, what's the sine of pi over 6? The sine of pi over 6 is 1/2. Therefore, the cosecant of pi over 6 is the reciprocal of 1/2, or 2. And that 2 is what goes right there. And so overall, the cosecant of negative pi over 6 is negative 2. And there's my answer. For all these questions, you first got to think about which quadrant is it in. That tells us if our answer is going to be positive or negative. You then got to visualize it properly to figure out your reference angle. Once you know your reference angle, you just have to go back to memory and think about what's the sine, cosine, tangent of that reference angle, and then piece all these things together. If you have these things memorized right here, and truly memorized, which means almost instant recall, then everything we're doing here gets so much easier. If don't have those memorized, this gets so much harder. Lastly, I'm just going to write down the answers to all of these, but how you can figure these out, these are all these angles here are multiples of 90 degrees. These are the boundaries between quadrants. All of these we can figure out by just visualizing an angle in standard position, but we can talk about that in class. That's it. I'm just going to give the answers to all of these. So the sine of pi is 0, cosine of pi is 1, the tangent of pi is sorry, I was thinking pi over 2. Cosine is 0. Let's try that all over again. Hey, how you doing? All right. Pi is 180 degrees. So sine is 0, cosine is negative 1, tangent is 0. Okay, also the same angle, 180 degrees, but now with reciprocals. Cosecant is going to be undefined. Secant is -1. Cotangent is undefined. For 3 pi over 2, which is 270 degrees, sine is -1, cosine is 0, tangent is undefined. Cosecant is -1, secant is undefined, and cotangent is 0. For 2 pi, the last stretch, this is going the same as 360 degrees, which is coterminal with 0. So all of these answers are going to be exact same as if I had a 0 instead of 2 pi, because again, it doesn't matter how an angle gets to a point, it just matters where it is. So the sine of 2 pi is the same as the sine of 0, which is 0. The cosine of 2 pi is the same as cosine of 0, which is 1. And tangent of 2 pi is going to be 0. And the cosecant of 2 pi is undefined. I should say is, not equals. Secant of 2 pi is 1, and cotangent of 2 pi is undefined. So all these can be figured out, like I said, for example, I don't know, let's pick cosine of 3 pi over 2. All these can be figured out in a way like this. Imagine an angle in center position. Visualize 3 pi over 2. 3 pi over 2 is an angle that goes around and stops directly right here. And then for this, we're between quadrants. So you can figure out cosine of this by just picking a point on here. The good thing is you can pick any point, which is pretty easy because your x-coordinate is always going to be 0. Y can be, I don't know, -1, let's say. Negative something. And which means the distance from here to here is 1. That distance I just drew in red. You know, and if I chose a y coordinate of -3, the distance here would be 3. It's always to be the same thing. But I'll stick with 1. And now, again, cosine of any angle is x over r. So in this case, it's 0 over 1, which is 0. Right? And I can do the same thing to figure out all of these things here by actually visualizing the angle in standard position, which is actually pretty easy to do if you actually draw it, because if you have an angle that's on one of these boundary points, it's pretty easy to pick a coordinate. One of your coordinates, x or y, is going to be 0, which makes your life pretty easy. All right, so I'm done there. Pretty extensive lesson. I should be quiet.